Hello again. Our next topic for the course is going to be a very important one this week on feature selection and extraction and a bunch of other related concepts about dimensionality reduction and manifold learning. This week is going to be an online lecture week of self-study. So we won't have the live sessions with recorded lectures like usual. We have pre-prepared self-study videos, which are available hopefully now is before the week that we're supposed to be doing it. If you look in the course calendar, in the course outline, you can see what's the schedule for this week. So I'm giving an intro lecture here, which is kind of brief, giving an overview of why we focus on this topic. And then our TA, Benjamin Gojo, one of my graduate students who's doing his PhD in this area and is quite an expert in the deep intricacies of the algorithms we're going to talk about, but even other ones that go kind of deeper. He's going to give an overview of most of the concepts because he'll give his own take on it, and he knows a great deal about this particular area. So the live sessions this week, I think we'll use them as office hour type things where Benjamin and me or the other TA could have some kind of back and forth to answer questions. But the idea is this week you watch the self-study videos ahead of time yourself, and then for the two live slots, we can use them as support times or answer other questions on Piazza, and it could be a way to go through problems to try to understand it, because some of these ideas are a bit tricky, and they get quite mathematically deep. The stuff that Benjamin would do will get kind of deep into theory, because that's how new methods in this field get created, and there's no way around it. There's conceptual abstractions that kind of explain what's going on, but the math is really where it's all coming from, because the idea is we're extracting information out of data, right? So if you think of the difference between data and information, data is like the numerical or textual or pixel representations on your computer. It's easy to collect data, but it's very hard to create information. So it's a subtle, almost philosophical kind of distinction, but it is also important that what I mean is philosophical is that the distinction between what's data and information is not in any way well defined. So data to you could be information to someone else. Information to you might be just data to me. So there's a bit of a subjective thing when that line is, so I wouldn't worry too much about that. But the important thing is to say you have some data you're given at the beginning, or that you have access to, and then you need to do some tasks with it, right? So most of this course is focusing on the later sections after this week are on algorithms to perform particular tasks like classification and clustering and prediction and object recognition and text analysis. In order to do that, you need to have some data available for the algorithm to work on. But in that kind of sense, it's better for the algorithms to work on already structured, meaningful information, where you know something about it, where you have the essentials or the important variations or information is readily available, right? So the deeper that the important information is hidden, the harder it is for your algorithm to find it, right? So feature extraction and selection is part of an entire area of trying to get meaningful information, perhaps more compact information or richer information out of some raw data. So we're going to get a bit of motivation about that and different areas that are in it. And then what I'm going to do is highlight the difference between these two particular words I'm talking about. I keep saying feature extraction and selection, but these are actually two different concepts. And we used to, in this course, spend a fair bit of time talking about feature selection, but it's actually not very complicated. So I'll explain the main concepts up to you here in this short lecture. And then Benjamin will do the rest of the lectures for this week on feature extraction, which are the mathematically more intense topics in this area. And he'll go through the fundamental concepts of them, a couple of the main different ways that feature extraction works. And we'll use those for assignments and topics later in the course because they'll become the basis of all of this, right? So if you think of the pipeline that we have, that we've done so far, we have your raw data coming in, right? So these could be, images or just numbers in a spreadsheet, or they could be text documents. We haven't talked about that yet, but we will. We haven't really talked about images much, but it could be many different types of things. And then we've talked about data cleaning, right? So you have missing data, you have outliers you may want to remove, and things like that. And then we talked about normalization, right? Or scaling. And these are all ways to make the data, like removing things that might be misleading, or missing, or filling them in, scaling and normalizing data so that it's really kind of comparable in the same style and measurement range, which again makes your algorithms a bit more possible to succeed, right? So these are all considered, at least in my structure of the course, pre-processing steps. In a sense, this is another pre-processing step, which is this feature extraction, selection, dimensionality reduction. I will explain what those are soon. I guess I could just put it here. So this is where we are today. But the goal at some point, as I'm saying there, is that you get your kind of structured, perhaps, information, and then this is where you do your data analysis or your AI or your ML task, right? And this will be a whole area, right? But before you can do that, you need to be able to structure. So this is the last step in kind of preparing your information for usage. So what's the motivations for this? We talk about, so this distinction between extraction and selection. So assume we have, we're given a data set X, and it's an n by d matrix, right? So we're going to have d dimensions and n rows, just like we normally have had before. And there's two things you could do. So what do you want to do? Say you could, the number of dimensions you have depends on the data that's been collected, right? So if it's census data, you've got information about people's age, their income level, their neighborhood they live in, what school they went to maybe, or, what languages they speak, or, how much property they own. There's all these kinds of information, right? If it's genetic data, the dimensions are, base pair sequences. So they could just be kind of represented as numbers or characters. If it's image data, the dimensions are the pixels, right? So for every image, you've got, 20 million pixels, there's 20 million features, each of them's just got a number between 0 and whatever your color range is. So, right, so the dimensions they could be lots of different values, there could be a lot of them, and they're really raw data, right? And so the idea here is to say, is there some way we could get a smaller number of dimensions, right? And then we'll start calling these features, right? So if we say data has just got raw dimensions, they're also features in a way if you use the raw data, but we want to have features where they're meaningful, right? And I guess the difference between that is just to say that that these are meaningful information, right? Now they could be, so one way you could do it with the census data, you want to do something that predicts demand for university applications in each neighborhood or region in Canada, and so you want to look at education levels of the parents in a household. You want to look at the income levels of that family because that's correlated with going to university. You want to look at the school, like the high school scores, right? So in neighborhoods where there's more people with high scores, or the high schools have higher academic standard, there might be more people from that neighborhood or city, applying to go to university. You're trying to make predictions on how many, applicants you're going to have. And there's a lot of numbers there that you don't need, but there's ones that are very relevant. So the one I talked about might be the relevant features you'd want to keep, right? So a simple thing you can do is to say, well, we're just going to select those ones. So the ones I mentioned, right? Income level, you could find the high school scores for that neighborhood. You could look at, obviously, ages, how many school-age children are graduating high school at that age, how many 18-year-olds are there, 17 or 18-year-olds that want to go to university in each kind of district. You could just take out those features that seem meaningful and ignore the ones that aren't, right? So maybe, spoken language at home is not important, or how many cars they have is not important, or the age of the parents is important. So you get rid of the features that aren't important. So selecting them is kind of the simplest thing you could do. And I'll go into a little bit of just overview of the methods people use for that today, because they're really not actually that complicated. They're kind of the things you would think of, although there are entire methods for doing it, like pre-existing algorithms. They're just essentially searching for what's the best subset of features to select out. If we think of it as a table that we've drawn, right? So we've got our n by d original data, right? And we've got rows with all our data files, and then the features, all the elements here are what we're talking about. In feature selection, we just want to take a few of these and pick them, right? And say, okay, here's our subset, and now it's a smaller set, and we'll name them. We'll have some features, F1, F2, F3, and we'll just call them that. And we'll use this for our algorithms. But in extraction, what we do is we transform this data into a new data set with completely different features, but ones that are more meaningful. And that's where the math comes in. So we do some analysis on this matrix, and if it's a matrix of numbers, we basically, the essential thing is you compute eigenvectors and eigenvalues of this matrix, and that tells you something about, directions within this d-dimensional space that are the most important in the sense of variance, right? So you essentially draw a new, you rotate the entire space of this data into one where you can rank the directions and say, well, if I only had 3 directions, I would pick these 3, and you use them. But these new features don't correspond to the original data at all. So the main distinction between extraction and selection is just that extraction, you are extracting new, meaningful, transformed features from the data. In selection, you're literally just picking columns, and the question is which columns that already exist should you pick, right? But they both do the same thing in the sense that they come out to be, you have a new set of features, and the new set of features, F, is smaller than the set of dimensions, and you do your learning on F, not on D. That's the idea of this entire week, basically. Why do we care about that? Right? Computers are powerful, chips are getting faster, Moore's law, etc. Why can't we just use all the data, all the time? First thing I always say when I'm talking to like a company or government person is saying, like, well, how much of this data do you want, and which parts are important to you? And I'm just like, well, here's my first statement is, let's not throw anything out. I never want to throw out any data, right? If we can find a way to store it, if we have to buy a petabyte server somewhere to keep all the data, let's do that, because you never know what you're going to need, and you might learn a better way to extract the information later. But you can't always do that. There is an enormous amount of data being generated every second, every nanosecond, and so you need to sometimes just reduce the amount of data. So there's a number of ways to reduce the amount of data you have, either for storage or actually even for performance. If we think about, and again, Benjamin will go into this again as well in his own way. If we talk about right the number of data points we have, right, it's the rows, it's the columns, it's also the dimensions. We'll often call them the features. The rows are the instances, right? They are the data points. These are all different words that mean the same thing, essentially. That we're talking about the rows and the columns of this table, which is the data. So if we want to make this data smaller, for whatever reason, there's two essential ways you can do it, and there's many other ways. We could say we can reduce the number of columns, or we could reduce the number of rows, right? So reducing the number of rows is not as commonly discussed. We'd usually call this data reduction. Benjamin has published a bunch of papers on this because it's part of his thesis. And so we won't get into that too much, but a lot of the methods we talk about with sampling already actually can be dealt with, can you use for that? Because you could say, let's just have less rows. Let's sample a bunch of rows randomly, or let's try to pick out which rows are the most important. Let's try to find rows that don't have very high mutual information and pick those. So there's various strategies you could do to say, let's reduce the rows, right? But it's not something people do much. They usually say, let's keep all the rows, because every new row, every new data point is a new instance, a new observation in the world. So these are somehow very precious, right? Whereas the columns, the data, the features, the dimensions, those all mean the same thing. These could be redundant, right? It could be easily be that these two dimensions are like highly correlated, right? And so you don't actually need both of them. So it's quite plausible that you can get by with less dimensions than you need, because they have lots of correlations between them, right? So I talked about we don't need to know how many cars a family has because we already have their income, right? Because they're highly correlated, right? If you have high income, you're going to have multiple cars, or you're not going to have multiple cars unless you have high income, right? Let's say that. So do you really need both, right? This is a problem that people get into because they'll try to use some dimension that they think is really uncorrelated, like say postal code, and say, oh, we use the postal code. That's just where they live. It has nothing about income or ethnicity or jobs. And then they'll use their learning on this. And people famously in the U.S. Had a criminal kind of monitoring system where they tried to be very anonymous and only use postal code, and it totally be completely biased towards African Americans, because in America it's very likely that you live in a neighborhood with people of the same ethnic background, and so all of the data in their database was racially biased, even though they're using this one thing, because this was correlated with everything else, right? So that's important. But that central idea of trying to figure out which columns and dimensions are the most independently useful, that's the whole idea. Dimensionality reduction then is this idea of reducing columns. That's the main idea here. So there's various reasons, like I said. It could just be obviously just to help you store it. If you have terabytes of data and you don't have terabytes of disk space, then you need to reduce your data. If you have, genetic data or image data, there's a huge number of dimensions, and so maybe you want to scale them down, right? If you reduce rows, that's a different problem. But it can reduce the cost too, right? So if you want to be training an algorithm and it takes time proportional, to the amount of data, and it usually takes, even worse, it might take, time like scaled in the data or something like that. Then you want to reduce the data as much as possible, right? Because the more data you have, the longer it takes to train. It actually turns out to be very helpful for visualization, and you'll see this a bunch later this week with Benjamin's discussions, because once you come up with a small set of important, useful dimensions, and you can create a plot in a small 2 or 3 or 4 dimensions and create an image that's meaningful, then you can understand the data better, right? Understand the data, the information that you have. And this is when you kind of are moving from the point of having data to having information, right? If you understand it, that's what's happening. Oh, I got a spelling mistake. There we go, fixed it. So another topic that will come up as you're going through The feature extraction part would be this idea of intrinsic dimensionality, though I think in research I don't see people talk about this that much, but it's trying to get at the idea of what's the fundamental minimum number of features to understand the data, right? And it would depend on your task, minimum number of features needed for some task. But it could just be even for some for representation, right? If you think of the field of compression, right? You're trying to make smaller files. You got your zip files, your 7-zip or whatever. It's a way of turning your data into a very small version, so that you can transport it more easily or store it more easily. And in a way, one way to do that is to figure out what is the actual essentials here, right? So as I'm talking about with data about populations, you could come up with a formula that maps, the number of cars people have based on income, or the likelihood of going to university given on income and family education level and neighborhood. And then instead of having those dimensions, that data about cars and university applications in your raw data, you just store the function and you could compute it again later, right? So those aren't intrinsic, right? But income level might be intrinsic because it really is one of the core facts about, a regional population. So that's that. And then part of what I was talking about before about complexity, I got to erase now, is this idea of the curse of dimensionality, right? So more rows makes it hard because you've got more data to process through, but usually an algorithm is not always, but sometimes it's linear in the data. So you get more data points. If you get twice as many data points, it takes twice as long to run, right? But usually, and that's not always the case. Sometimes it is, as I was showing, like polynomial in the number of data points. But very often it's not linear in the number of dimensions because you might have to do comparisons between all the dimensions. So this, one way people talk about this is the curse of dimensionality, which is a phrase you should be familiar with. It's really just a term. It was introduced by Richard Bellman, who's very famous in many different fields, but an anchor of many things of my other course on reinforcement learning, my undergrad course. So Bellman comes up a lot. But he had this other phrase he made at one point to explain this idea that as the number of dimensions goes up, it doesn't just increase, the difficulty of a problem may not just increase linearly, it might increase exponentially. So part of that is reason is just an information-theoretic point of view, is that if you want to fully represent, say, a 10-valued function, right? It has 10 dimensions. It take on 10 different. A function takes on 10 different values. Then, in order to fully represent it, you'd need a table, right, with your n inputs for all the inputs you could have, and 10 columns to literally represent it as all the values. If you wanted to turn a function into a table, you'd need a table with n by 10 dimensions, if that's how many outputs the function has, right? Even though the function itself only has one dimension, right? It just takes this single input and has those mappings, right? So say now then there's a vector of 20 numbers as your input, right? And this is your input of your table. How many columns would you need now to represent it? Right? If you think about every one of these inputs is a vector of 20 numbers, and you still only have even 10 data points. So even if there's only 10 rows here, but each of them could be a 20-dimensional number. So you don't have more data in a sense, right? There's only 10 points, 10 distinct values this function takes on. But now they're in a 20-dimensional space, right? Whereas before they were essentially points on a line, right? Here's the line, and the function has defined points here, and everywhere else it's maybe has some particular value. And so the thing is that here you'd need 10 to the 20 because you'd still need to represent for every one of these possibilities what the value is, right? right? So in a similar way, if we want to take a sample of a data set and get some kind of representative sample of the space, if there's more dimensions, we need more samples. Every time there's a new dimension, we need as many samples as we had before for every new value in that dimension. And so if there's a lot of algorithms, we'll talk about the difference between parametric and non-parametric algorithms. But essentially, some algorithms, the more complex the data is and the more detail you want, it adds more parameters. It keeps creating new variables to fine-tune its understanding, right? And so these types of algorithms need more data to train, and the more dimensions you have, the more data you're going to need. So if you just think about this in terms of a visualization, right, we've got our original 1D function here with a bunch of values, and the question is, how many data points do we need to fully represent this, right? And maybe you're happy with a certain approximation, and so you just need, 1 or 2 or 3 data points from each of these clusters, and then you'd be able to define your function as saying, well, as long as you're within these ranges, then the value is given, and if you're somewhere else, the value is 0, right? But if you fully wanted to represent it, you'd need as many points as there are data points in your function, right? It's still going to scale linearly with that, even if we have that approximation. It'd be n, 1/10 of n or something. But if we have now a two-dimensional function, now so for every one of these x values, essentially, we have a y value, and it's in 2 dimensions. Now we need to be able to figure out, okay, where is it in x, but also where is it in y, right? You want to be able to create kind of bounds and boxes around these areas. How many variables are you going to need to represent that? Right, so in order to do that, we're going to need values for something proportional to n to start with, but then for every one of those values, we'll need something proportional to y, right? So if we're trying to do it exactly, we would need n squared of these, right? Because we'd have to represent all the points here at a granular enough level and all the points here. If we're trying to do it approximately, then it would have to be proportional to n squared, because we'd still need to cover enough areas in this y direction, right? And so, and the curse of dimensionality is any kind of domain like that where as the number of dimensions increases, the difficulty of the problem is going to get much worse. And this happens anytime when you have to do comparisons amongst the dimensions, right? Or pairwise comparisons or evaluations, right? So if you ever need to do something like, for every x, something about y, and it's some kind of calculation, and it's like, even if it's just like rank the values, is x less than y, or is it similar to the mean of the values in the other dimension? If you ever need to have some relationship between the x's and the y's individually, then as d increases, your complexity is gonna increase as well, right? And it's gonna increase, in some kind of relationship where, very roughly, the number of data points is going to increase exponentially for every dimension you add, right? Because this is just for one, but if there were millions of points, you'd have to do this for all the pairs. So there's another phenomenon that occurs, especially in engineering. You might have lots of observations and sensors and readings, and you're trying to optimize some machine's performance. And say you maybe don't have that many detailed observations of it, but there's many sensors and it's continuous. And this happens also with genetic data or text data, where you've got a very large number of dimensions and features, but you might not have that many data points. And so if you optimize your system to fit the data you have. And we'll talk about overfitting and trying not to overfit your data so that you just basically only do well in the data you've seen. You always want to generalize so that you can do well in data you haven't seen, right? But even beyond that, if you're trying to correct for overfitting, you can still get to the point where more features would actually hurt you because certain features, these are the kind of the, like I was talking about, the intrinsic ones. Maybe there's a certain level of, like, the intrinsic may not be completely well defined, but it's somewhere here. The number of features you really need to describe the problem. And at this point, you start getting redundant features that repeat other things that are correlated with other ones, and you start seeing patterns, right? So people see patterns in faces and clouds because it's kind of this infinitely complicated shape, and we're very creative. Your algorithms could be the same thing, right? So there's lots of data. There'll be correlations randomly just between these things, and eventually it's going to see like, oh, I got some other way to fit it, and your algorithm will try to fit all these other features which are not that important unless you weight them properly or get rid of them. The simplest, best weighting is just to get rid of them, and so your axis is going to go down, your arrow is going to go up because you can start chasing shapes and clouds, right? And so essentially, at some point, you do want to cut off how many features you have, because more features is not always better, right? More data is almost always better, but more features is not necessarily almost always better, because the features could be misleading, or they just could be have random correlations, right? There's so many features, you're going to see some patterns that aren't there, that aren't essential. So as I said, there's kind of two primary approaches or philosophies for reducing your data, reducing your dimensionality, and it's just extraction and selection approaches. And there's no reason you can't do both. So feature extraction, which you guys will talk about more for the rest of this week with Benjamin's lectures. The idea is to combine the original features and to come up with a new set of features, to extract something, to transform or project the data to some different space and get a new way of looking at the data, new features that give you more compact, rich information. You have to have some kind of objective. This says what you're trying to optimize for. So the new features you get are not any way more correct than the original data. They just let you see the data from a particular perspective. So this projection idea is really a useful way to think of it. That it could be, imagine you've got some very high dimensional data set, and I can't draw in 8 dimensions, but imagine I could, and you've got your data points everywhere. And if you're projecting it down to 2 dimensions, you want to say, is there some relationship here where they are all in some useful pattern, right? And that the data points that have some commonality in the higher dimensional space are all close to each other, right? So things that are close here in a meaningful way are close in this lower dimensional space. And then you can understand it and deal with it better if it's in this 2D version, right? That's kind of one of the essential ideas. How do you do that for each data set? Transformation produce new features. It may even be relevant to the meaning of the data. So we'll see that in text processing, that will come up with a small relationship, like a low dimensional representation of the data here. And that an arrow here might actually mean something, right? So like being the child of someone else would be like, you'd actually move in this direction on the graph, and it'd be more likely that this data point is a child of that data point. That would be great. It's not always happens, but sometimes it happens. So we can interpret the dimensions and understand these graphs and our features better. So the goals of it are going to be create lower dimensional representations, help us better describe the data, especially the variance. That's the first thing you'll talk about. But also to be able to discriminate or distinguish, right? To discriminate means like to separate points, right? And that's exactly what classification is, right? So in this data set, if it's easy to discriminate, then you can basically, where to draw a line so that you can say these are parents and these are children. That line is something you can write out simply with a low dimensional function. That would mean it's easy to discriminate. So you want to come up with a representation, even a visualization where this is true, right? So feature selection, just to dive into that a little bit more, is, like I said, trying to find the subset of features that is just better, closer to this intrinsic value of the dimensionality of the data. Hopefully, as I said, you're trying to get rid of irrelevant features or redundant features, right? So ones that repeat other data or are highly correlated with other data. And it will still be more interpretable because those dimensions now mean something, but it may not usually be as big a deal as when you've done this extraction approach. So the main ideas, which I'll just highlight really only up to here to give you an overview, and if you want to read more, you can read more about the others. These will be like extra topics, not tested or covered on the course, because I think there's more important stuff for us to focus on. But it is useful when you're being a data scientist and be able to do it. It's kind of thing you should be able to just come up with and look up the best practice and use it. So you can rank the features. You can basically figure out which of these dimensions is the most important, right? Like I was saying, maybe my theory is that, my hypothesis is that income would be the most important, one of the most important ones in this census data for a lot of tasks. So you'd come up with some objective function to help you score the dimensions and analyze the data in them, and then rank them. And then you keep, the top n, the top 5, the top k of the dimensions, and only use those, right? But then once you have a ranking, you may not just want to pick the top k of them. You might want to pick the top k such that none of them are highly correlated, right? So how do you search for that subset? There's a whole literature of different ways you could search, right? Like I said, it's not actually super complicated. We want a subset of features. Let's say we have n samples, d features, and if you start thinking about it as subsets, there are 2 to the d possible subsets, ways you could pick the columns, right? Obviously, we've got d columns, right? So we could pick just column 1, or we could pick column 1 and 2. We could pick column 1 and 3 and 5. All the combinations of this, and including having all d, gives you 2 to the d. So it's a search problem. And there's different ways to do this ranking. So that first part that really a lot of them are based on is come up with some way to rank all of the features. There's a bunch of different methods for doing that. Like I said, you got to have some quality measure or objective. So why do you need it? If you're trying to discriminate between classes, then you want a ranking that is good, that helps you with that, right? And then select the best m features. That's what I'm talking about. So this can be an issue because you're essentially evaluating all the features individually, right? Which means that you're not capturing kind of correlations between them. So what about correlation? So in this plot from the Kevin Murphy textbook, he's got a bunch of different data sets. Some are just lines, some are Gaussian clouds, some are nonlinear shapes, and computing the correlation coefficient of all the data and showing it above. And what we can see is that we can get this number, the correlation coefficient of our data, and it can be useful some ways, right? You can say, well, okay, this one has kind of a slope in that direction, and this one has a slope in that direction, and so we could figure out that, we could rank features along a certain direction in terms of importance, or maybe, in alternate directions to make sure we cover it. And we know that if something is like basically zero correlation, it's just going to be noisy. But all these numbers on these images are the same, right? So you can have a correlation of 1 and have the slope be completely different, right? So this correlation coefficient doesn't really tell you the degree of the slope. It tells you the direction of it and maybe whether it's flat, but not the intensity, and that may or may not be important. It can tell you the noise, kind of the spread, right? So you got a difference between, how spread it is and how slope it is. So you can get this kind of variation. But then all these ones on the bottom, these all have correlation coefficient of 0. So the points have been chosen in a way that they essentially cancel each other out. And so even though you have very interesting nonlinear patterns here, they still give you the same numbers as these. So you wouldn't be able to distinguish these two data sets using correlation coefficients directly, well, from this straight line, right? So it's not rich enough for us. So what else is there? So rather than just simple correlation, a more effective thing that people would do in this area, and then you could use in many cases, is to look at more information or probabilistic comparative measures between features, dimensions, to figure out which ones you should choose, right? So we've talked about a bunch of these. We go back and look at the probability stats review lecture. You can find out more about these different measures if you're not familiar with them. The mutual information in particular, I'll just talk about. Makes a lot of sense because this, if you remember, you've got the mutual information between two vectors, which is basically trying to say these two vectors are generated by some distribution. How similar are they, right? How much information do they share? How much information would you lose by using x instead of y? That's one way to look at it. But it's also kind of the distance between, we have this KL divergence measure, right, which we talked about in that review lecture as well, which is gives you a kind of dissimilarity between the joint distribution of two vectors and their under two different assumptions: an assumption where they are correlated and an assumption where they are not correlated, where they're independent, and saying, well, what's the distance between these two, right? So if there's a distribution that explains them being correlated, what's the correlation matrix? What's that distribution? If there's a distribution that assumes they're independent, what would that be, and what's the distance between them? That's what this mutual information does. Like I said, you can also think of it as what is it? How much would you lose? How much information would you lose by approximating y with x in terms of distributions? But it's straightforward to compute if you have these numbers. You can compute the probabilities for these just statistically from the numbers you have. In our case, for feature ranking, we would compute the mutual information between the features. So for some feature f, for some column of the data f, and for every data point I, you'd have this xi, and yk are the target class labels, right? So it's the thing that you're trying to do. This is the right answer, what you know you want to be true. So in our case, with the how many people are going to go to university, apply to university in this neighborhood or city, it might be a number, or it might be a true or false thing if it's on an individual family basis. But you have something you know is the right answer, these labels, and you're using that, the distribution of those, which is the truth, and say, I'm going to approximate it with this subset of columns, right? So I'm going to use these 5 columns that I think are important, and that'll give me some distribution of values. How does that compare to the true distribution of the target that I want? Right, and so it may not be that the features you pick here that have high feature response are like the most likely or the most correlated with the label, but they might be very helpful in distinguishing that label, that class, right? And so it's more complex than just a correlation probability between those features and the label, but it gets at that. It might be more useful for you. So that kind of thing gets used in feature selection, and you can use other distance measures to kind of evaluate them. But then once you've already done that, there's all these other things about, well, how do you structure the subsets? Do you have subsets that are basically inherent on the data that talk about the variation and structure of the data itself, or do you look at ones that are trying to maximize your accuracy on a task like classification, like we were doing? So those give you these two different filter versus wrapper approaches, which has an entire set of options you could have. You could also be talking about whether you're using objective functions that are tied into the data directly, or mixing and matching based on the feature. And then once you're searching, you can use any kind of search algorithms and strategies to do that. You can basically, that's why I didn't want to necessarily go into these, is that you could be adding features, you could be removing features, you could be looking around for a nice size of subset of features. So the way you iteratively search for the right subset could be done in various ways that are more really software engineering kind of strategy here. And one might work better based on your data than others. If you have a very large number of dimensions, maybe you start from 0 and add features that seem the most meaningful according to your mutual information score or some other score. But if you don't have that many features, you might just be saying, well, which are the 10 features I can trim off, right? So you'd start from all of them and remove some. So there's various strategies you could follow there. And if you're interested and want to read more into that, you can do that. So that sets up then for the other larger field of feature extraction, where you really have to invent new features and transform it and find these projections that I was talking about. And you're still going to say, I want the most significant set of small features, because you want to have a lower number of dimensions than you started with, right? So if you've got 1,000 dimensions and you extract 1,000 dimensions or 10,000 new dimensions, you have a lot of new dimensions, and they might be very informative, but you're not helping with your cursive dimensionality. So you usually want a smaller set of that, right? A lower dimensional subspace, which is what we say. So the subspace is the combination of your data points in the number of dimensions, the number of features you have chosen. And so you want that to be smaller in terms of dimensions. We've talked about before that it should hopefully be more interpretable, but it may not be. And so what you're going to go through are basically linear methods and nonlinear methods for finding patterns and variations in the data itself. Many of these are unsupervised, so you're saying, let's look at variation, the eigenvalues, the standard deviation, local structure, and figuring out what's the right way to group points together in terms of space. But they can also be supervised. You can say, here's the labels, I want you to find me the best, smallest representation of this data so that I can solve this problem properly, whether it's prediction or classification or something else. And there's many different ways to do this, which you guys will get into. And it is a really essential building block for the other algorithms and being a successful machine learner or data scientist or engineer, because a lot of times you do need to reduce your data, and you need to know the standard ways to do this and be able to find the resources to extend your knowledge once you've done this course as well. So hopefully we'll be able to set that up for you this week with a good baseline understanding for dimensionality reduction and feature extraction. Thanks.